I'm Anil Kumar. Welcome to my series on complex numbers. In this video, we'll discuss how to represent complex numbers as position vectors. So we have been talking about complex numbers z being represented as a plus bi. Now we can also write the same complex number in column form a and b, right? So this form helps us to perform operations, especially addition and subtraction, very simple and is used many times. So we are going to actually use this nomenclature and then show how to add and subtract complex numbers. So we'll also refer to two different ways of representing the complex number, where one is, we'll say, a position vector. So if I represent a vector whose A is the value along the real axis and B is the value along the imaginary axis, so in this case A and B, this vector could be AB if this value is A here and that is BI. So a directed vector with tail at the origin, so that's the origin. So what we are saying here is a directed vector. You can say directed segment with tail at the origin. Right, a tail at the origin, and length of segment equal to magnitude of vector. Normally magnitude will be the absolute value written like this. In this case the magnitude will be a square plus b square square root. Correct? So that is the directed vector and we call this as the position vector. Perfect. So we are going to represent our complex numbers as position vectors shown here, and then we'll also see how to add and subtract vectors. So to add and subtract, we'll have two different ways of doing it. So if I have a vector, let's say this is one vector and the other vector is kind of like this, in that case we could add these vectors by forming a parallelogram, right? So in that case the vector which is the diagonal of this parallelogram is sum of these two vectors. So if I have vector u and a vector v, then this vector is u plus v. To find the difference, we could actually have the other diagonal. So if I sketch the other diagonal, which is, let us say this, then this vector will be u minus v. Is it clear to you? So that method is parallelogram, right? So that is parallelogram. And we also have a triangle. So in triangle, you actually place the tail of the other vector on the head of the first one. So if this is my u, then the vector v, which will be translated so that its tail is on this, and the sum of these two vectors will be shown by the third side of the triangle. So that becomes u plus v, right? If this is your vector u and the other vector is v. So we'll now in details understand what we just talked about. So we'll talk about complex numbers in different forms, and then we'll show how to represent the complex numbers as a position vector. So let me write few complex numbers here. Let's say z equals to 2 plus 3i, right? So that is a complex number. This number can be represented on this complex plane also. This is referred to as Argand diagram. Where this horizontal axis is the real axis and the vertical is the imaginary axis, origin being at their intersection. The complex number z, 2 plus 3i, will be represented with 2 along the real side, 3i, and so that number is basically the complex number 2 plus 3i. Now, you can also represent this as a vector. So let me say the vector z could also be written as, we can write this as 2, 3. Now, we are writing this as a vector in column form, and we are going to represent this as a position vector on the complex plane. So we'll write this as a position vector. So when I say position vector, it really means that the tail is at the origin, right? So we say tail at the origin, right? So if the tail is at the origin, and now we need to sketch this position vector, then be represented by a segment with direction, right? So this directed segment, we can call this as O to P, for example. So we say OP is representing the position vector 2, 3. So it is a directed segment, as you can see on this complex plane. So that is the way to represent complex numbers as position vectors. So when we say complex number, so remember, when we say number, it means a point, correct? And this point is this point P. And when we say position vector, it means this segment, directed segment, right, with the arrowhead. So vectors have magnitude and direction. So the magnitude of this vector OP is given by the length, and this is equal to, in this case, square root of 2 square plus 3 square, which will be square root of 4 plus 9, or square root of 13. So this length will be square root of 13, which represents the directed vector OP. So I hope that makes sense, right? Now you could represent any vector written in many different forms on a complex plane. Now let's write down few vectors and represent them on the complex plane. So we could have a vector z equals to minus 3i. So if I write z equals to minus 3i plus, let's say, 2j, where I and j now are the unit vectors. So in this case, when I write like this, so this complex number, in this case, I and j are unit vectors. So that complex number can also be represented here as minus 3i means 1, 2, 3, and 2j means this. So in that case, when you are representing unit vectors I and j, then basically this becomes vector j and that becomes vector I. So I've kind of mixed this up. However, when we are talking about the complex numbers, we'll prefer to write this as minus 3, 2. So that is your complex number. Now when we say represent this as a position vector, in that case we kind of draw what we had shown here. So minus 3, so minus 3 on the real axis and 2 on the imaginary axis gives you this arrowhead, which represents that vector. So in this part of the video, we have learned how to represent complex numbers as position vectors. So remember, position vectors will have a tail at the origin and a directed segment. Length of the segment is proportional to the magnitude of the complex number. Perfect. Now, let us also see how to add and subtract complex numbers when they are represented as position vectors. Now let us take an example to illustrate how to represent sum of complex numbers. We are considering position vectors. Okay, so let's say we have a vector u, which is, let's say, 2 plus 3i. We'll normally write this vector as u as 2, 3. So, and we can sketch this vector 2 and 1, 2, 3. So this vector from the origin represents the position vector u. So that's the origin for us. This is real axis and that is imaginary axis. Let's take another vector v, which can be, let us say, let's say 4 minus 5, which we will write this as 4 minus 5. And then we'll try to add these two vectors u and v. The result will be 2 minus 4 and 3 minus, add means plus, right? 2 and 4. Add the corresponding x values and the y values. 3 minus 5. And the result will be 6, and that is minus 2, right? Let us see on the complex plane how this is performed. So now, the vector v, which is 4 minus 5, will be 1, 2, 3, 4. 1, 2, 3, 4, 5, right? So this vector, the position vector will be from the origin to this point, right? Now to get the resultant, we try to complete the parallelogram. So the step here is to complete parallelogram, then diagonal from origin represents sum u plus v. Is that clear to you, right? So let's do this. So drawing a line parallel, which is from here, 4 minus 5, we can go from here 1, 2, 3, 4, 1, 2, 3, 4, 5, right? So that should be connected to form a parallelogram, correct? So we know the opposite sides are now parallel in the diagonal. From the origin of this parallelogram represents the sum u plus v. Is that clear to you? You can clearly see that the result here is 6 minus 2 as expected. Perfect. So that is how you actually add the complex numbers using vectors. We'll again do the same thing, but this time we'll use a triangle to perform the addition. So now let us see how to add vectors using triangle. Now both methods are commonly used. So the idea here is, let's take some example. Let's say u is equal to, let's take a vector which is, let's say 2 minus 3. So this vector u is 2 minus 3. Let me sketch this. 2 minus 3 means here, right? So this is the vector 2 minus 3 for us, the vector u. We want to add to this the vector v, which is, let us say, equals to, let's say we have 3, 5. So now, if you want to make a triangle and use triangle to perform the addition, then the vector v is placed with tail at the head of the u, right? So place tail of vector v on the head of u. Perfect. And then we have a vector 3, 5. So from this position, we go 3 units right, which is the real part, 1, 2, 3, and 5 up. So 3 and 2, 5. So that's the vector v. Correct? Now the resultant u plus v is right there. So u plus v will be the vector shown here. So that vector will be u plus v. Is that clear to you? This is from the origin O. This is our real axis, and that's the imaginary axis of our complex plane. You can also see that u plus v will be 2 minus 3 plus 3, 5, which is 2 plus 3 is 5, and this is 2. So you can note here 1, 2, 3, 4, 5, 2, right? So this vector is indeed 5, 2. Is that clear to you? So that is how you can perform addition of complex numbers when you are using the vector method, right? So using a triangle, that's how we can actually add them. Now let us see how to subtract the complex numbers, again using position vectors. Let's take an example here as u equals to, let's say 3, 4. Let me write like this only. And v equals to, let me sketch. So u is 3, 4 for us. So we have 1, 2, 3, and 4. 1, 2, 3, 4, right? So that becomes the vector u. Three, 4. Now we want to subtract the vector v. So let's take this vector as minus 2. Let's say minus 2 minus 3. Okay. So I'm going with the space which I have. So vector v is minus 2 minus 3, which will be represented as minus 2 and minus 3. So that is vector v for us, correct? So we have vector u and vector v. Now if I have to perform the operation u minus v, these are vectors, then the result will be, as you can see, 3 minus of minus 2, 4 minus of minus 3, and what you get here is 5, and that is 3 plus 4 as 7. So that should be the result. Now, how do we do it geometrically? So basically, what we are going to do here is we are going to add, when I say u minus v, it is same as adding negative of v to vector u. So let me sketch negative of v here. Means rotation by 180 degrees, right? So instead of minus 2 minus 3, now it will be 2, 3. So that is negative of v. So adding these two, we get our result. Now the addition can be performed by completing the parallelogram. Perfect. So let's make a parallelogram now. So from this point we will go 3, 4. Sorry, this was 3 minus 4, right? We went down 4 steps. So this is minus 4. So minus 4 plus 3 is minus 1, sorry. So this should be 5 minus 1. So I've sketched it downwards. That means it should have been minus 4, okay? Right. So now let's complete this. So from this point we'll go 3 minus 4. So 1, 2, 3, 1, 2, 3, 4, and that will be a vector parallel to the vector u. Perfect. As you can see, we can now complete our parallelogram, and the diagonal of this parallelogram is the difference of the two vectors, right? So this is u minus v. Is that clear to you? Correct? So treat minus as addition of the negative vector. So that ways you could use what you learned earlier, how to add vectors even to subtract vectors. So I hope that makes sense, right? So this is the origin, that is your real axis, and that's the imaginary axis. Perfect. So that is how you would actually subtract the two vectors. So with this we come to an end of learning how to add and subtract complex numbers using position vectors. Perfect. I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.